Okay. First of all, thanks to the organizer for having invited me. I'm sorry that I couldn't manage to come in person. And I think after the very nice, very interesting talk by Werner, now we move to something lower in energy. Probably you know what is Fluka. Fluka is a code which exists since now many years, but has quite a lot of applications in cosmic ray physics. You have probably seen Tuesday afternoon the presentation by Ralph about our application for predicting neutrons in cosmic ray showers, but as the code has many, many other applications. And I will try to concentrate today mostly on the things which could be somewhat peculiar or of interest for this community, where Fluka is often used inside Corsica as the so-called low energy generator. So this is just a tentative sketch of what I'm going to present. Probably I will not manage to present everything, so I apologize in advance. I will give a minimal introduction to the Fluka hadronic models with some recent developments. I will spend some time on real and virtual photon interaction, like it was pointed, I think, already on Monday, on Tuesday by Sergei. Quite a lot of muons and neutrons come from photonuclear interaction in cosmic ray showers, so they are really very important. And I would like also to spend some time in showing how Fluka manages muon propagations and interaction. And probably many of you do not know that the code can also do nicely neutrino and antineutrino interactions. Last but not least, I will speak a bit about recent developments in the interface with Corsica. I will not speak at all about low energy neutron transport. That is a very specialized topic where Fluka is very good, but it's probably not particularly interesting for you. It's more related to nuclear applications. So that's just a scheme, not very simple, of how the Fluka interaction models, they really are combined together. We have a model called PNUT that manages hadron nucleus collisions below 15 TeV lab energy. It does also photonuclear, virtual photonuclear, electronuclear, muon photonuclear, neutrino interactions. All of that is done there. And then we have three other models dealing with nucleus-nucleus interaction, DPM Jet3 in the latest version by Anatoly. In a quite evolved version of our QND 2.4 and the Boltzmann master equation model at low energies. I think for today, I will mostly concentrate on this part. Since we had this discussion a few moments before, I think I will just try to underline like final state effects like ray interactions, formation zone, evaporation, fragmentation, etc., are important, at least for some observable neutrons, but not only. Another things that I would like to underline, because I think nobody touched it, is that as a nuclear physicist, I have always difficulties in accepting a description of nuclei which doesn't take into account Fermi motion, which has a strong effect at whichever energy. So interaction in PNUT, I start from low energies. You have on the, this is just examples. On the left side, the double differential distribution for various angles from 15 degrees up to 150 degrees for 800 MeV protons on iron. Symbols are experimental data, in this case, I think from Los Alamos. And the histograms are, there are several experiments there. And the histograms are our model prediction. On the right, you had the same free GV on lead in this case. What is important to stress is that the parts, the high energy part of the spectra, they are at those energies where you really don't have quark chains, strings, etc., are dominated by cascade pre-equilibrium emission. And the low energy part, which is essentially isotropic, is dominated by evaporation. So if you want to do neutrons, you have absolutely to have this kind of process of final, say, initial and final state processes into your descriptions. Only, I will come on this back later, and I think Ralph already touched this point on Tuesday afternoon. Only very few neutrons, even in very high energy interaction, they really come directly from string or chain hadronizations. Since we were touching a formation zone a few moments before, just to show you what, for example, Fluka does, of course, in Monte Carlo, you can play. And if you decide that you have no formation zone, which of course is highly unphysical, if you look, for example, at the rapidity distribution of charged particles produced in 250 GeV pion collisions on aluminum and gold, you have the top plots. So nothing comparable to experimental data. If you introduce a formation zone, which a typical approach that is in Fluka is exactly like it is in this formula, you get something which is nicely reproducing the experimental data. Fine. Look, please, at the green peaks that they are protons. That are, let's say, in the old emulsion terminology, are gray protons. The experiment didn't see the very low energy particles. You will never get this kind of particle unless you have reinteraction, rescattering with intranuclear cascade and preequilibrium after the fast instantaneous multiple collision part, Glauber-Gribov part. Hadronization, that's why I'm touching this point, because it's something that we have recently changed, like almost everybody else probably, trying to catch with the raw issues in meson production. The Fluka hadron-hadron interaction model is based on the dual parton model for the string production. And then Fluka has its own chain hadronization model for which at very low invariant masses goes smoothly into a Fermi breakup-like phase space explosion. You have just an example with very old data on this plot, a 6 and 22 GeV. Feynman X distribution of positive pion for pions on hydrogen. At even lower energies, non-elastic hadron-hadron interaction are managed by a resonance model, 1 or 2 resonances depending. As you know, there is a surprising large yield of ROS, in particular of neutral ROS, measured in pion nucleon and pion nucleus experiments in the formal region. And not only this, much more worrying, if you want, the ratio ρ0, pi0, omega is strongly rapidity XF dependent. That's, I think, has been discussed already many times those days, which, if you want, it contradicts what was one critical and in the past generally assumed constraint of hadronization model, that once the quark content is the same, things are the same. So you would expect naively for this sort of universal hadronization that the spectra of these three mesons should be proportional one to the others, which is not true. So also in Fluka, these things have been evolved. That is just an example of what has been done. This is the situation. This is Na22. I think this data has been already shown probably before. In green, you have the ρ0. Red pi zeros and blue omegas. These were the predictions before changing the hadronization. And as expected, omega and rho zeros were proportional one to the other. In principle, also pi zeros, but of course you get pi zero after, because of the case of the other resonances, you get much more in the central region. And that is on the right side, the pi minus on carbon, this is Na61 going to ρ0 and omegas, again, before. And after we change the hadronization, that is the present situation, which is much nicer. Of course, there is a price to pay. We absolutely conserve isospin in every single step. I want to stress this. I don't like not conserving isospin, even for the ROS. The ROS, they should conserve isospin exactly like the pions. But of course, we had to assume that the hadronization of valence quarks is different from the one of C quarks. That was more or less what we did. If you look at the inclusive distribution of pions, forget the resonances, same experiments. You have positive particles, negative, and pi zeros. That was left the situation before, right, the situation after. And there is a change, of course, in the forward region, as expected. And okay, that is where we are. One comment. I'm skeptical that one is getting many more pions out of this, because if you conserve isospin, then we can decide that we violate isospin symmetry, but if we conserve isospin, we get an increase in the rho zeros, but we must have an increase also in the rho plus and rho minuses, which in turn produce pi zeros. And so what we gain from one side, we lose from the other side, more or less. This is just an example. Fluka is typically used, for example, in Corsica below, say, 200 GeV. Depends, I think it's a threshold that the user can set as they like, but Fluka can still do reasonable jobs up to much higher energies. You have here an example with ISR. So, for example, the right plot corresponds to roughly 2 TeV in the lab. Above 10, 15 TeV in the lab, we switch to DPN Jet 3, as I told before. We did a lot of work also on cross-section recently. A couple of years, no, I think 3-4 years ago, we introduced into our model color transparency, so cross-section fluctuation, as you like. I think you know what it is. Among the say, there are too many advantages of this, apart that is physically meaningful. Sorry, one moment. At the same time, it provides a way to account for inelastic screening for free, if you want, and it helps in reproducing better multiplicity distributions. Of course, it's not easy to introduce in the Glauber formulas, but can be done exactly. And Monte Carlo helps a lot in this. On the right plot, you have the multiplicity distribution for negative particles, for positive kaons on aluminum and gold. And the red and dark blue curves are after the introduction of cross-section fluctuations, while the orange and light blue are before. Please take into account that the multiplicity average are more or less exactly the same. It's just the distribution that changes. At the same time, now, Linux can compute cross-sections with Glauber, etc., and both elastic, non-elastic, say, particle production and quasi-elastic cross-section up to the highest energies. This is just an example, a comparison that the, say, calculation are the line and the symbols are various experiments. But of course, we have also a lot of comparison at lower energies with lead, carbon, and a lot of other stuff. So we are pretty confident in our cross-sections. And now let me move to try to convince you that which of these ingredients are really critical for neutron predictions. First of all, Fermi motion and actual isotope by isotope binding energies. In a simplified nuclear description, the residual excitation that you leave inside your residual nucleus is fully determined by the depth of the hole that you have put in the Fermi sea. If you don't have a Fermi sea, I don't think you can compute any sensible excitation energy. Excitation energy then, taking into account that binding energy are changing isotope by isotope, are the critical ingredient for producing all low energy neutrons or also low energy protons, alpha, whatever. Internuclear cascade, the reinteraction due to internuclear cascade are important because they contribute to the excitation energy and they produce the famous quasi-elastic peak here that you can see always in all neutron spectra together with pre-equilibrium. So this is a plot of our calculation of neutron spectra in the atmosphere for proton, iron, and photoprojectile at a given energy. And actually, the neutrons that come from really hadronization, primary, say, production, are very few. You can see here the antineutrons, and they are the same. This part comes really from intranuclear cascade and pre-equilibrium. The rest, they come mostly from evaporation, and then, of course, not with this shape. Then this shape is generated by the moderation into the atmosphere. A few words on photonuclear interaction. They have been deeply revised recently in Fluka, quite a lot of work. We take into account the giant dipole resonance interaction. For example, here is an example for carbon-12. There are plenty of data. The data, by the way, are the green points, and the Fluka cross-section are the black curve in this case. This is the giant dipole resonance region. This is the quasi-neutron region, the delta region and other resonances that more or less disappear in nuclei, and then the vector meson dominance. All of this is cast into Fluka, into the PINU framework. So, of course, we have internuclear cascade, pre-equilibrium, evaporation, and some specific effects which are typical of the nuclear environment for photons and pions, and that I'll discuss in a moment. And at the same time, Fluka can also do muon photonuclear interaction, electronuclear interaction, and electromagnetic dissociation, something that I think somebody called ultra-peripheral collisions the other day. So why photonuclear interaction are important for cosmic ray cascade? Because, for example, in our calculation for these energy protons, say of the order 5, 10 to the 18 eV, roughly in between 16 and 20% of the muons, they come from real or virtual photonuclear interactions. 16 if we use Sibyl star, 20 if we use less pion, say rich, less muon-rich codes. 1/4 of these muons, that is surprising, they originate from muon photonuclear interactions. I mean, from pions, kaons producing muon photonuclear interaction. And roughly 70% of the neutrons, they come from real or virtual photonuclear interaction, with the GDR regime, where the cross-section is large and produce low-energy neutrons, particularly important. Out of these neutrons, roughly 1 out of 7 comes from muon photonuclear interaction. Okay, on the right plot, you have the plot of the photonuclear cross-section in the region below 2 GeV for several nuclei. If you exclude protons, deuterons, helium-3, helium-4, all others, they fall exactly on the same curve when you take the cross-section, divide by the number of nucleus. So you would expect naively that the description of photonuclear interaction in nuclei in this region is simply one, for example, photonuclear on a proton times the number of nucleons. Not at all. This is just a plot, for example, of the photonuclear cross-section for nitrogen-14, and the one for on the proton multiplied by 14. Apart that, of course, there is a smearing of the resonance due to Fermi motion, etc. The number of pions is completely different. In nuclei, photons can be absorbed on 2 nucleus and 3 nucleus, and these channels are huge in the delta region. For example, if you do the same plot for lead, there will be only 23% pions per interaction at the peak of the delta resonance, contrary to 1 for gamma on protons. So it's essential to take into account the nuclear effects for photonuclear interactions. At higher multi-GeV energies, Fluka includes, of course, the process C, which is virtual meson dominance mediated with Glauber, Gribov, etc. treating here I put rho could be a rho could be a phi could be a omega with the relative probability, but it takes also into account coherent say scattering of the virtual vector meson, the virtual vector meson, and quasi-elastic scattering that now we can compute correctly out of Pinot, and the effect of quasi-elastic is important. Here you have the spectra computed for as a function of the form momentum transfer for 470 GeV muons on calcium and on hydrogen. Below you have this experiment, Fermilab, I think. Unfortunately, there is no absolute normalization in the experimental data. And on top, you have our simulation where you can see in blue the coherent part, in red on hydrogen, where of course coherent or quasi-elastic is the same. And on calcium, you can clearly see also the quasi-elastic quasi-coherent part, which is very important, is exactly more or less the same level as the other. And this produces rho zeros, which decay in pi plus, pi minus. So you just transform a photon into hadrons with no pi zero in this case. So it's a channel which has to be taken into account. Let me move to electromagnetic dissociation. Electromagnetic dissociation, I suppose you know what it is the situation where you have, for example, two colliding nuclei and one of them breakups in the electromagnetic field of the other. This has been introduced in Fluka a few years ago, at the beginning because there was a long-standing polemics with our colleagues at Langley when we were doing some calculation for NASA. They were claiming they were very important for showers in the atmosphere. In the end, it turned out it was not true. But at the same time, it was very useful because they were important for LAC. On the right plot, you can see the lines are the Fluka prediction for the cross-section for electromagnetic dissociation for lead-lead collisions, and the purple symbols are the experimental data of Alice at the square root of S of 2.8 TeV nucleon. And you can see that the code is really nicely able to predict correctly the cross-sections and also the split in 1 neutron, 2 neutron, the rest. On the left, you have at 150 GeV per nucleon. These are SPS data. Again, lead projectile on several targets, from light ones to very heavy ones. Again, the cross-section as predicted and as measured. Perhaps I will go very fast, just fragments producing the same interactions, where the yellow part is what comes from nuclear interactions, in this case DPM jet-free, with the Fluka evaporation and breakup. And the purple one is what comes from electromagnetic dissociation. Of course, when you have a lead on carbon, electromagnetic dissociation is relatively minor, because in this case we are looking at the lead dissociation. And of course, lead dissociation goes with a z square of the other nucleus. So this is very big on lead-lead, where you can see how much electromagnetic dissociation matters. So the next question is electromagnetic dissociation important for ultra-high energy showers or not? I don't have the answer. Here I have just for you some cross-section that probably are not completely wrong, as predicted by our models. You can see it is split in projectile dissociation, that's probably what one is more interested in, but also target dissociation. Target dissociation, of course, produces low energy particles, but you can see that roughly speaking, in half of the events, you have pions produced. And the cross-section are not huge because air is relatively light, but still are comparable to the particle production absorption cross-section. So we have not arrived at the conclusion if it is really worthwhile to include this process also in Corsica in the future through the Fluka interface. Preliminary estimation is that the muon and neutron production is not really too much dependent, but other observable could be, we have still to investigate. Very rapidly, some example of what Fluka can do for muons. These are very old data. We used in the past, in the mid-90s, the Atlas calorimeter test to take data with muons. And this is just the minimum ionizing signal in the calorimeter, in the electromagnetic calorimeter, lead liquid argon, and in the hadronic calorimeter of Atlas, iron scintillator. And here in the next plot, you have on the bottom, this time the energy loss spectrum in this case is, sorry?
5 minutes left.
Okay, thank you. Thank you. For 300 GeV muons in Atlas, and so you can see that the code can reproduce very nicely. This is dominated by pair production and Brestram. Of course, we did the same with electron. And that is a completely different case. These are the neutrons measured, the neutron multiplicity measured in Borexino from cosmic ray muons in Gran Sasso underlying lab as computed by Fluka. The difference between the two Fluka versions is just the introduction of EMD, also for muons. And you can see that the code can nicely reproduce the number of neutrons produced also underground. Antineutrinos in Fluka. So Fluka can do quasi-elastic resonant production, deep inelastic scattering with antineutrinos. These are just an example of the cross-section as computed by Fluka for an isoscalar target compared with experimental data and compared with more recent, very high energy data from IceCube. You can see that within the very large error bars of the experiment, things are reasonably reproduced. And this is, if you want the more interesting, is how charge current, new move charge current events distribution of energy in the Icarus detector with a sent to Gran Sasso beam in the past, left on the right for neutral current events. I would like to remind that the VUL-C-NGS beam has been computed, optimized, etc. with Fluka from the target up to the neutrino flux to Gran Sasso. The interface with Corsica probably is something that you are interested with. There exists an interface with Corsica where Fluka can be used for non-elastic hadronic interactions since I think the end of the 90s. 2000, 2001. It was done by myself and Dieter Eck. And has been recently much more evolved with very important help by Tanguy. The present interface, the revised interface, which is now, I hope, complete, is more flexible. All materials and compound can now be managed, not only air. Of course, in Corsica 7, only air, but in the future in Corsica 8 also, whichever other material. In principle, it can deal also with elastic and quasi-elastic scattering events. I think it's not activated by default. It can deal also with electromagnetic dissociation if we arrive at the conclusion that is important. It can do electro and photonuclear interaction as well. On the, if you want a symmetric line, now Fluka has been interfaced with EPOS LAC and with CBIL 2.3D, with or without star, and maybe in the future with QGS jet, exploiting the CRMC environment kindly provided with the help by Tanguy, etc., in such a way that we can cross-check what the two codes do, Corsica and Fluka, in similar situation, and understand if some things are important rather than not. Very rapidly, just to show a couple of recent applications of Fluka. This is, for example, the moon in gamma rays produced by cosmic rays impinging on the moon, as computed by Fluka and as observed by the Fermilab satellite. And you can see the agreement is very nice. And Fluka is also used to produce tabulation of inclusive cross-section for interaction of cosmic ray isotope on nuclei up to iron, and have been these data have been using the Dragon 2 code to study galactic cosmic ray propagation. If you are interested in the details, you can look at this paper. Thank you, and I hope I'm not too long.
Thank you very much, Alfredo. So we have still time for some questions. Sergey?
Alfredo, thank you for the nice overview of Fluka. Actually, we are very happy to hear about new developments, in particular regarding the photo production. But could you please clarify a few things? Coming back to the photo production, you mentioned a couple of processes. I'm not sure I understood what is what.
Yes, which slide? Tell me.
You had some real and virtual photonuclear interactions.
Yes. Yeah.
You had some list, and then you had muon.
Yes. Photonuclear interaction of muons. Yes. And photonuclear interaction of muons, we do combining two approaches, the Bezer-Bugayev approach with our cross-section, and the low energy, if you want, EMD applied to the GDR, quasi-deuteron, etc. And that is, yeah.
Where you have essentially say with VMD, and there you speak about rho-zero elastic path naturally. I had a question regarding that slide. Maybe next.
This one.
I think so. Yes. Here you are essentially in the VMD region. Of course.
Yes. Of course. Yes.
Of course, you have elastic path. It's total cross section after all, right? You have elastic path or quasi-elastic producing just rho-zero. You have normal inelastic final state. But here you also speak about virtual. Here, or maybe next slide, you spoke about virtual for the production. This I
yes, because you see in the.
What do you call virtual photo production? Virtual photon.
In this case, I'm simply speaking about the example is with muons, where of course you have virtual photons which are emitted for doing these processes. So if you want, this is muon going into gamma star, interacting with a nucleus, in this case, carbon and proton.
You speak about the direct photon interaction. Not converted into, if you move to very high energies, indeed, this direct component becomes important.
But this is still a virtual in the sense, this is still VMD. I want to be clear. That is, we are still at energies, say these are 470 GeV muons, so the spectrum of the virtual photons produced by the muons is still peaked not much higher than a few tens of GeV or probably even less.
Should be miserable at low energies. It's only important once you go to PVs or whatever. And here you also speak about coherent, incoherent. Would you please just give a number? Let's say how many % you get incoherent of the total?
Of the total, you mean? Of course, it depends on the nucleus. What I can tell you is that at least in this specific case, calcium, the incoherent part is more or less the same as total cross-section integrated over T as the coherent part. And both together are roughly, if I remember well, but order 20-30% of the total.
I would have expected order of magnitude less from just
if you think take whichever, for example, pions, coherent and incoherent elastic scattering of pions on nuclei. For light nuclei, they are typically 20% of the total cross-section. For heavy nuclei, they can arrive even at 30-40%. So there is no reason to expect anything different from rho-zeros.
Maybe these are low energies. In case energies are low, I would tend to agree. if you move to high energies, things change drastically.
Yeah, but don't get, I don't know how to say, cheated by hadron proton, because in that case, elastic is really very small. But on nuclei, elastic is mostly geometric. In the limit of a black disk, elastic must be 1/2 of the total cross-section. That is well known.
Sorry.
But last question, you spoke about electromagnetic dissociation.
Yes.
How many percent do you have for this contribution of the total inelastic?
I go back to this here. It depends, of course. Look, for example, here for Alice, lead, this energy, electromagnetic.
I'm sorry, Alfredo, iron, not lead. Lead, obvious.
Okay, here, oops, sorry.
If we can
Sorry that this you have a number here. Yeah, you have roughly half a barn at this energy per nucleon, 10 to the 18.
Agree.
Yeah. So half a barn projectile dissociation, 1.5 barn target dissociation. So the two together is 2 barn, is comparable to the particle production. Of course, it's completely different, the final state.
It is
Yes.
Z proportion. It is order of magnitude rule.
Yeah.
Sorry to
Of course.
We are running already out of time, so we have to close the question session. I don't know if you want to add something very, very fast, just to end.
No, I think.
So, so we close then the participation for this session or questions. So thank you very much, Alfredo. We thank to him.